I'm Judee Burgoon from the University of Arizona, and I will be speaking today about uh, our automated tools for multimodal deception analysis. And in keeping with the international complexion of this organization, this will be a smorgasbord. And there's been some talk about the uh, lack of success using nonverbal behaviors as predictors. Some even declaring that nonverbal deception detection is dead. But I think you'll see after I finish this talk that's a premature declaration. So let me tell you first about the data set that I'm going to apply these tools to. This is from the SCAN Socio-Cultural Attitudinal Networks project conducted by 6 universities across 8 locations, 3 of them in the US, University of Arizona, University of Maryland, University of California, Santa Barbara, and 5 international sites. And basically what happens is people show up at our location, and around a table, they choose chairs, and that seating makes a random assignment of people to a role as either a villager or a spy. And in this game, the villagers are going to conduct missions, and the spies are going to try to sabotage them, presumably by deceiving. What's important for us now today is the multiple sensors that are collecting data. In front of each person is a tablet that collects audio visual signals. Then we have overhead a 360-degree camera, and finally off to the side a profile web camera. So we're collecting a lot of sensor data. And these are going to include nonverbal behavior, verbal behavior, and linguistic analysis from the texts that are captured. First, starting with the nonverbal behaviors, we have a tool we're using that's OpenFace that collects kinesic facial expressions, head pose, rigidity. And this is an open source tool. That means anybody could choose, not just researchers, download it and use it to do analysis. Then the other tool that we're using right now is Amazon's Recognition, which can help detect emotional states. So here's an idea of what OpenFace collects. They create bounding boxes around heads. Those are the boxes that square up around a person's head and face. And from this, they're able to extract eye gaze vectors, head poses. This would be the nod, the tilt, and the shake of the head. And then landmark locations where all those red dots appear. So you can see that they can detect such things as, let me go on, I'll come back to that in a moment, eyebrows, eyes, mouth, and jaw. And we use those to conduct some other analyses. Here's the OpenFace action units. There are 18 of these. And the AUs can detect both the presence or absence of an emotion, and then it awards an intensity value on a 5-point scale. You can combine some of these AUs, these are the segments of the face, and combine them to arrive at certain emotions. So for example, down here is surprise, and it needs segments 1, 2, 5, and 26. And you will see part of it here represented in this bottom left picture that has the eyes for the AU1 and AU2. We do with some of these features other analyses. One of them is facial rigidity analysis. And so here you'll see the regions that have the landmarks: brow, eyes, nose, lower lip, full lips. And what we do is calculate from the tip of the nose the distance to all these other points. Then we calculate the movement along those regions so we can get the dynamics. And finally, we can calculate how rigid or immobile those movements are. So this becomes what we're calling rigidity analysis. So if we want to combine all of these features together, and these are again all nonverbal features, can we detect if they are significantly discriminating between deceivers and truth tellers? In one respect, they are. Deceivers turn out to be less dominant than truth tellers. They are more rigid in their face and head pose. They have less intense facial action, and they show less positive emotions than the truth tellers do during the times when the truth tellers, the villagers, are winning a mission. So you can actually spot the deceivers simply by identifying who is exhibiting these behaviors. Now, you might want to know, how well can we predict then who are the deceivers versus the truth tellers? We can do this by applying one of many different classification algorithms. That's what's over here on the left. Oh, I'm so sorry. And column A shows you what happens if you only use eye gaze and head pose. Column B shows you what's happening if you use the AUs and rigidity. Column C shows what happens if you add in emotions. And if you do a full analysis, which is in the orange marked square, you'll see that you get much better results, to the point that down at the bottom where you have the ensemble, the combinations with the top two features, you get accuracy of almost 67%. So what this tells us is both we're better off combining all of the features and also using a combination of classification algorithms. But 67% probably isn't the best we can do. And by the way, if you are interested in these slides, you'll get the rest of these details, but F1 is actually the combination of discriminating truth versus deception and seeing if you're more accurate depicting deceivers or truth tellers. But we're going to do better if we add some other features. And so the next area we go to is vocalics. This is every part of the voice other than the words. And for this, we use another tool called OpenSmile. OpenSmile is another software package, freely available as an open source tool, and it will extract speech-related features like loudness, pitch, voice quality, and also summary features like means, peak durations, onsets, and so forth. So for our analysis, we're extracting all these features you see here on the left, mostly pitch, loudness, voice quality, the harmonic to noise ratio, and jitter and shimmer, which are variabilities in loudness and fundamental frequency. One of particular interest to us when we're talking about dominance is the turn at talk. And the turns at talk can be measured as how many there are or the duration. And in this case, we decide to look at turns at talk to see if deceivers are more dominant and or less dominant. And in this case, uh, the prediction was that deceivers will try to be more uh, non-dominant, try to hide in the weeds, if you will. And in terms of turns at talk, that was true. The blue lines are villagers, the red lines are the spies, and across the rounds, we see that the turns at talk for the deceivers, that's the spies, is consistently lower. And the same thing is true if we look at the duration of these over here on the right-hand side, and you'll see that almost consistently the spies have shorter turns at talk. So here again with the voice, we're seeing some indications that deceivers are being less dominant. We would probably also, though, like to include not just the nonverbal indicators, but some of the verbal indicators. And in this case, we're using a tool developed at the University of Arizona called SPLICE. And this is structured programming for linguistic cues. It has a number of different output features, parts of speech, quantities, uh, calculations of things like text complexity, verbal sentiment, and so on. It can be used either as a web service or used offline. So here are some of the features when we're looking at dominance that are on the left-hand side here. And over on the right-hand side is which ones emerged as significant if we do a regression analysis. The ones in red are the ones that came out as significant. Number of words was significant, and also the dominance ratio, which is a combination of a number of these features. So here again, we're seeing that deceivers are behaving in a different manner than truth tellers, and we can automatically detect these. Now, if we can meld all of these things together, it's probably going to be even more powerful. And so we have two techniques we're currently using to combine all these features: retrospective attention-based analysis and critical point analysis. The critical point analysis does this because in long group interactions, you've got a lot of talk time that is procedural, where deceivers are also being truthful, where other people are talking that has nothing to do with the actual issues at hand. So we go to what are the critical points, like during this game, people have to nominate leaders, and then the facilitator has to announce who is being selected. Those are LN and RA in the bar graph over here on the right. Those are all the blue ones. And so what we do is we take this critical point analysis where we pick the critical point, and we look at the 3 seconds beforehand and the 5 seconds afterward and use that as the point of analysis. And over on the bar graph, if we aggregate across the entire group, the red and pale blue bars show you what we get for accuracy with aggregation. But if we only use the critical points, we get the blue ones. And so we can get up to 83 or 85% accuracy if we are using just the critical points. The other analysis that we are starting to use is the retrospective analysis. And here what we use is a pipeline that extracts, again, FAUs. These are emotional features, and they're extracted. And each one has a waveform and can identify this waveform and then go back and pick the segments where deception has taken place. So we'll give you an example of this. You'll see the person here, we're going to have 8 seconds of analysis. And you're going to see on the right the actual waveforms for nose wrinkler, upper lid raiser, and blinks. And you see the movement of his face. So we can extract just the important segments there and not only know that deception took place, but also extract how it took place, what were the behaviors that were entailed. So this is just a sampling of what we are currently doing with multimodal uh, deception detection tools. The bottom line is that these automated tools are a great benefit for deception detection, whether you are a practitioner and working with somebody who can identify what these behaviors are, or they're familiar to you, and also for researchers to identify the points at which deception is taking place. So with that, I'll open it up for questions.